All right, so we're ready to start our next unit, which is on similarity. And so we're going to talk a little bit more about similar figures a little bit later on, but just thinking about the word similar, right? The word similar means alike, but not exactly the same. And so we're going to apply that definition to geometric figures a little bit later on. But suffice it to say that similarity has a little bit to do with being proportional, right? Not necessarily the same size of objects, but same type. So we're going to lead into this talking about ratios, proportions, and then introducing something called the geometric mean because it fits in with the conversation on proportions. Okay? So you should be able to set up and simplify ratios. You need to be able to use ratios for different applications, and I'll show you how to do that. You should be able to set up and solve proportions, and you should be able to find the geometric mean of two numbers by the time we're done. Okay, so first things first, simplifying ratios. We simplify a ratio, like for this first one, 64 meters to 6 meters. And that's how we read that, right? And so you see your definition box here. It says ratio is a comparison of two numbers written as, right? And so you can write it as a fraction. So a ratio can look like a fraction, but it's really not a fraction. We don't want to treat it the same as we do other fractions. Or you can write it with a colon, and either way they're going to be read A to B. We're comparing A to B. And so a ratio is our way of comparing two different measurements, two different quantities. All right? So if we have the ratio of 64 meters to 6 meters, right, we can write this as a fraction. The meters will divide out, and we can reduce 64 over 6, which is 32 to 3. Okay? Now think a little bit about what a ratio tells you. What is a ratio trying to tell you? Well, let's think about not this ratio specifically, but just any ratio. If we had a ratio that reduces down to 3 to 1, what that tells you is that the quantity, the first measurement, the first whatever, the first amount, is 3 times larger than the second one. That's why 3 to 1, right? And so if we're looking at this as 32 to 3, it's a little bit tougher to pick out that meaning. Now, that is a reduced ratio. 32 to 3 is a reduced ratio. If you're ever asked to simplify a ratio, you would get 32 to 3 and you'd be done. Okay? But to make it more meaningful, I think we ought to divide it out to where there's a 1 in the denominator, and you would get 10.67 to 1. If you divided the numerator and the denominator by 3, that's how you would make the denominator 1, then you would get 10.67 to 1. And so what that would tell us is that 64 meters is over and not quite 11 times longer than 6 meters. It's over 10 times longer than 6 meters. And that makes sense, okay? Versus if you reduced the next ratio, 5 feet to 20 inches. If you just reduced the fraction, you'd get 1 to 4, which apparently that means 20 inches is 4 times longer than 5 feet. Think about that. That can't be right, right? So we can't just reduce it. The issue is they're not in the same units. And so very often you want your unit, not very often, a ratio is more meaningful when they're in the same units, right? So we need to convert one of these units over. And to do that, we need some unit analysis. So I'm going to convert feet to inches. It's usually better to convert the bigger measurement to the smaller. So I need a conversion fraction to do that. Right? In my conversion fraction, I need to set my units so that the feet will divide out. So right now feet are in the numerator. I need to put feet in the denominator of my conversion fraction. And I'm changing them to inches, so I'm going to put inches in the numerator. And that way the feet will divide out. Now we can fill in with the numbers. In 1 foot, there are 12 inches. So now we multiply the two fractions. 6 times 12 is 60 inches to 20 inches. Reduce that down, and we get 3 to 1, which means that 5 feet is actually 3 times longer than 20 inches. And that makes a whole lot more sense. Okay, so make sure that your units are the same, and then you can just reduce down your fraction. And typically we reduce it down just far enough so that we don't get decimals in the numerator or the denominator. Now I know I did that over here for the 10.67 to 1, but I was trying to illustrate what a ratio is trying to tell you. So understand that if you're asked to reduce a ratio and it reduces down to 32 to 3, that's the answer choice you want to go looking for. That's the one that's going to be listed. Okay? All right. Here's a couple more for you to try. Simplify those down. Stop the video. You can check your work once you start it back up. Okay. So what did you get? 24 yards to 3 yards. We can just make 24 to 3, reduce down to 8 to 1. And it's important that you don't drop the denominator. Yes, 8 over 1 as a fraction is the same thing as 8, but we need to see both amounts there so we know how the comparison works. What this tells us is that 24 yards is 8 times longer than 3 yards. Okay? Now, the 150 centimeters to 6 meters, we need to convert. Right? I'm going to set my meters on the numerator and the centimeters in the denominator so the meters will divide out. In 1 meter, there's 100 centimeters. So these meters will divide out, and we'll have 150 to 600, and they'll both be in centimeters. So when we reduce that down, we get 1 to 4. So 6 meters is 4 times longer than 150 centimeters. Okay? Good. Now, how can we use this idea of a reduced ratio? Well, you're planning to paint a mural on a rectangular wall. You're able to measure the perimeter of the wall as 484 feet. And that the ratio of the length to width is 9 to 2. Now, that doesn't mean that the length is 9 feet and the width is 2 feet. What that means is when you write them as a ratio, they reduce down to 9 to 2. Let's think about that for a second. What do you do when you reduce a fraction, right? Let's look at this one. If we go back, we reduce 60 over 20. How do we get to 3 to 1? Well, you're dividing out a common factor. 60 and 20 have a common factor of 20. So I can rewrite 60 as 3 times 20 and rewrite 20 as 1 times 20 and then divide out that common factor. Okay? That's what we do when we reduce. So what we know right now is that the length of this wall is not 9 feet and the width is not 2 feet. What we know is that the ratio of length to width is 9 to 2. So what that means is that they must have had a common factor. The length and the width must have had a common factor. So if I draw out this wall, the length and the width had a common factor. Now, we don't know what that common factor is. So in math, anytime we don't know what something is, we let it be an x. And so since they each have a common factor of x, then I can multiply the ratio, 9 to 2, by x in the numerator and the denominator. And what that tells me is that the length is 9x and the width is 2x. And since I know the perimeter is 484, I can find that common factor by adding up my lengths, 9x plus, now don't forget that this is a rectangle, so there's going to be 2 lengths, and there's going to be 2 widths. So 9x plus 9x plus 2x plus 2x has to equal 484. And when we add that, we get 22x equals 484, divide by 22, and x is 22. So that means that the common factor is 22. To find the actual length and width, we need to plug that in up here. 2 times 22 is 44. 9 times 22 is 198. So the length is 198 feet, and the width is 44 feet. Now, it asks you for the area. So we're not quite done, right? Area is length times width. The length is 198. The width is 44. And so when we do a quick multiplication of those two numbers, we do get 8,712. And that's area, so it's going to be in square feet. Okay? So trying to apply these ratios into helping us find some of the things that we need. Okay? Same thing if we have something called an extended ratio. In an extended ratio, we've managed to find three quantities that had a common factor and divided that common factor out between the three quantities and reduced them down to a particular ratio. Right? Excuse me. So for example, in this triangle CDE, we know the angle measures reduced down to an extended ratio of 1 to 2 to 3. Okay? If that's the case, then that must mean that those three angles had a common factor. We don't know what that common factor was, so we're going to apply a factor of x to all three of these. And so now we can take 1x plus 2x plus 3x and set it equal to what the angles of a triangle have to add up to. And that is from math for as far back as you can remember probably, the sum of the angles of a triangle is 180 degrees. So 1 plus 2 plus 3 is 6, and we're ready to go solve. Divide by 6. And so x is 30. And if x is 30, then we can apply that factor to all of our angle measures and make this guy 30 degrees because it's 1 times 30. This guy is 2 times 30, or 60 degrees. And this guy is 3 times 30, or 90 degrees. And so there are your three angle measures. So again, the moral of the story is we're applying an x factor to our ratio because when we reduce a ratio, we're dividing out a common factor. And then we're using what we know. Right here with the angles of a triangle, they have to add to 180. All right? All right, a couple of practice problems here for you in your notes. Go ahead and work those out. Stop the video and see if you get the right length and width for number 3 and the angle measures for number 4. If you're not, got to come in and see me and we'll figure out why. Okay, so you should have gotten the length to be 14 feet and the width to be 10 feet. And the angle measures for the triangle in number 4 should be 20, 60, and 100. If that's not making any sense, come in during STAR and we'll figure it out. Okay? Now, moving on. A proportion by definition, and there's the vocabulary box in the top right corner, it's when we take two ratios and we're able to set them equal to each other, right? So if I were to say something like the ratio of 1 to 2 and the ratio of 3 to 6, those are the same, so we set them equal and we've just created a proportion. Okay? Now, there are a lot of different properties to proportions, and we're going to talk about that again in just a minute. One of them is called the cross product property. And that means that if I multiply the diagonals, 1 times 6 is 6, 2 times 3 is 6, then I can set those equal to each other. Should be able to do that in a proportion. So that's sort of the reason why we get to a proportion and to solve it, we cross multiply to solve. Okay? So in these two proportions, we're going to do the same thing. We're going to cross multiply and solve. 10 times x is 10x. 5 times 16 is 80. Divide both sides by 10, and x is 8. Piece of cake. No problem. Okay? Well, same thing over here. The only thing I'll warn you about, 1 times 3y is 3y, is that you make sure you distribute this 2. 2 times y is 2y, 2 times 1 is 2. Subtract 2y from both sides, and y ends up being 2. Okay? Solving a proportion, piece of cake. Just some things that you want to keep in mind. All right? Got some practice problems down here at the bottom for you. Give those a shot, start the video, and make sure you're right. Okay, did you get 16 over 5? You might have gotten 3.2. That would be okay. 12 and can't see, there's 6. Okay? Again, if you're not getting there, make sure you come in and we'll figure out why. Now, to help apply these proportions, as part of an environmental study, you need to estimate the number of trees in a 150-acre area. You count 270 trees in a 2-acre area, and you notice that the trees seem to be evenly distributed. So that's our way of saying that if I compare the ratio of trees to acres, those ratios should be equal, right? So in other words, since I've counted 270 trees in 2 acres, I can write a ratio of 270 trees to 2 acres. That ratio should be equal to a ratio comparing the number of trees in the whole forest, which we don't know, to the acreage of the whole forest, which is 150. Now, this is what I'm talking about when I mentioned that proportions have a lot of different properties, okay? There's something called the reciprocal property, where if you have a proportion that's true, if you flip both ratios over, the proportion's still true. And there's a lot of other properties. Now, all that is to say that you might see setting up a proportion makes sense in a different way than what I do. Since there's about 6 or 7 different properties, there's going to be about 12 different ways to set up a proportion to get you what you need that are all going to be just fine. You've got to try pretty hard to screw these up, okay? The bottom line is, as long as you make sure that your 2 ratios are comparing the same things in the same direction, in the same order, then your proportion is going to be just fine. Some of you guys may see this differently already. But anyway, this is how I see it. So I'm going to cross multiply. 2 times x is 2x. 270 times 150 is 40,500. We're going to divide by 2 and get 20,250. So there must be 20,250 trees, or about 20,250 trees. Okay? All right. Now, the geometric mean. So the part of this that you're probably not as familiar with. The geometric mean. If I asked you to find the mean of 2 numbers, you would tell me that you'd add those up and divide by 2. Because mean is average. Mean is the same thing as average. But what you may not know is that average, that type of mean is called the arithmetic mean. The geometric mean is different. The geometric mean, and you see it right here in this box. The geometric mean of 2 positive numbers, and you're going to understand why they have to be positive when we start doing these, but the geometric mean of 2 positive numbers is a positive number that satisfies this proportion. Okay? In other words, if I want to find the geometric mean of 24 and 48, then what that means is if I compare 24 to a particular number, and then take that number and compare it to 48, those 2 comparisons would be the same. They would be equal. So we'd be able to set this proportion up. And it's the x that we're looking for. Okay, now I know what this says over here, and I don't want to do it this way. There is a shortcut. When you find the geometric mean of 2 numbers, there is a quick way to do this. But if you will get into the habit of setting up this proportion every time, this will make your life so much easier when we go to right triangles next semester, okay? So set the proportion up every time. That's the definition of the geometric mean, so let's keep doing it, right? So I'm going to cross multiply and solve. X times x is x squared. 24 times 48 is 1,152. 1,152, okay? Now, to solve for x, which is what we're going for, we're going to square root here and here. Okay, square root of x squared is x, and then we have the square root of 1,152. And at this point, we've got to stop typing this into our calculator and getting a decimal answer, because if you get a decimal answer and then you round that decimal, you're no longer at the geometric mean. It's not as accurate. So we've got to get good at reducing our radicals, and that's what we're going to talk about now. You need to reduce the square root of 1,152. Now, I have a method that I think makes sense, and I'm going to show that to you right now. If you have a method of reducing radicals that gets you to where you need to be and you like it better, then use it. It's fine. But here's what I do. I put 1,152 in an upside-down box, and I'm going to start factoring this down. And it's kind of like doing the factor tree, but it lines your factors up a little bit better. I'm going to divide this by 2 first. I know 2 will go into it. It's going to go into it 576 times. Then I'm going to divide this by 2 again, which is going to go 288 times. Now I'm going to divide that by 2 again. So which will go into 144. And 144, I can divide 2 into it and go 72. I can divide 2 into 72 and get 36. I can divide 2 into 36 and get 18. I can divide 2 into 18 and get 9. I can't divide 2 into 9, but I can divide 3 into 9. And I want to keep going until this number down here is a prime number. And I'm there, right? We need to keep factoring down until we get down to a prime number. Now, you can divide by any prime number. You can use any prime number as a factor. 2, 3, 5, 7, anything like that at all. All right? Now, here's the deal. And you've probably heard other teachers talk about this before, but it takes 2 to break out of jail. It takes 2 to break 1 out of jail, right? Why is that? Well, because if you're breaking out of jail, you're probably getting shot at, and so you're going to need someone to take a bullet for you, right? So in other words, this 2 has a buddy that is going to try to help him break out of jail and take the bullet for him, so he's going to get shot, right? These 2 buddy up and try to get out, and he gets shot. These 2 buddy up and try to get out, he gets shot. Now, this last 2 doesn't have a buddy. He's not going to try to break out of jail. I'm not going to try to break out of jail unless I have somebody with me who might take the bullet for me, right? But this 3 has a buddy that's going to take a bullet for him, so that 3 gets out of jail. Now, the radical is jail. So, he gets out, he gets out, he gets out, and he gets out. So a 2, a 2, a 2, and a 3, and then a 2 had to stay in jail. So I'm going to have this radical 2. Now, anything that you pull out gets multiplied together. Anything that stays in gets multiplied together. So this 2, 2, 2, and 3 all get multiplied together. 2 times 2 times 2 times 3 is 24. The 2 stays in. So 1,152 reduced down as in a radical is 24 radical 2. Okay? Whatever method you want to use, you need to reduce your radicals. If you don't understand that one or can't remember any other method, make sure you come in and see me, and we'll figure out the easiest way for you to do this. Okay? All right. So you got 3 examples down here below, 3 practice problems. Give those a shot. Stop the video, start it back up, and see what you get. Okay. So, the answers you should have gotten are 18, 18 radical 3, and 12 radical 2. Now, that's if you can reduce your radical. Did you set these up correctly? The geometric mean for 12 and 27 is a number that if I compare 12 to that number and then that number to 27, those comparisons have to be equal. Right? And then we're going to cross multiply and solve, and so x squared is equal to 324, and you got to reduce that. Same thing for number 10. 18 to x has to be equal to x to 54. Cross multiply and solve. Then you need to set up 16 to x and set that equal to x to 18. Cross multiply and solve, and then reduce your radical. Again, if you need some help with that, come in and see me, and we'll get it figured out. Okay? That's it for today. You got your homework out in Canvas. Make sure you have it done by next time.